So, the next bit of information we need, each of these half reactions should produce some kind of energy. And energy is necessary in order to make the electrons move one way or the other. If we separate the two half reactions, we can capture that energy and make it move through a wire, make it move through some kind of device. Okay? So, one of the reactions we have is with lead oxide.
Sorry, Mr. Martin, did
Yes.
you restart the iPad?
Yes. Okay? Yeah, it's blinking. So, one of the reactions we're looking at involves lead oxide and sulfuric acid and produces some electrons and all that sorts of thing. And it creates a certain amount of energy. Okay? And that amount of energy, make sure I'm looking at the right one here. That's this one. Is 1.69 volts.
Where did that
Comes from a table in your book, which we'll get to in a minute. Okay? 1.69 volts. Okay? Now, the other one basically involves converting elemental lead in the presence of an acid to lead 2+. Okay? And that produces 0.13 volts of energy. So we might ask the question, how much energy total does this thing produce? Okay. Now, when we talk about energy, volts is not really very much an amount of energy. It really represents something just ever so slightly different. Okay? That leads us to the next thing that we need to talk about. We'll come back and look at this momentarily. Okay? So, V, or volts, is a measurement of something called electrical potential. Electrical potential. Okay? Now, there's another related quantity called amps. Okay? And you may remember that amps is one of those 7 fundamental SI units. It measures electrical current. So voltage doesn't measure current, it measures a related quantity called potential. The best analogy I can give you is this. Think of a water hose. There's a certain amount of water that flows through it, and there's a certain pressure at which the water comes out. Amperage would represent the amount of electricity. Voltage, the potential, represents how much force is pushing that electron. How strongly those electrons are being pushed to move from one place to another. That's why it's referred to as potential. It's kind of another comparison. It's compared to potential energy. This is like electrical potential energy. How much potential, how much drive is there for the electrons to get from one place to another? Okay? So amperage and voltage are related. We won't talk very much about amperes for another couple of days. Mostly what we're worried about is voltage. Okay? Now, we typically will use this character. It's like a cursive letter E. And after right now, you'll hear me refer to this as fancy E. Okay? Fancy E is what we will refer to as electromotive force.
What's the degree sign, not sign?
Well, we're getting to that. But yeah, that has to do, it's kind of similar to delta G with that and delta H with that. Okay? It sort of implies standard. So this is the standard electromotive force. Okay? Or we can also call this the standard reduction potential. So how many of you have with you today that pink packet I gave you early on in the year with all the stuff that goes along with the AP exam? Complete with one page in there that you've never used yet. Look at that page that you've never used yet. How is it labeled? What does it say at the top, Sarah?
Standard reduction.
Standard reduction potentials. So when you ask me where those two numbers that I just wrote up on the board came from, they came from a table like this. Okay? So what that means is, if you can identify what's going on in a redox reaction, and you have a table like this that you can look on, you can determine the voltage that that thing can generate. Now, we have to take into account one other thing. Let's step back for a second to what we're talking about here. Does the fact that we have a mole of lead or a mole of lead oxide here making 2 moles of lead sulfate total play into it? Does the fact that it generates 2 electrons play into it at all? Okay? The short answer is no. The quantities in these reactions don't make any difference. Because fancy E, electromotive force, is an intensive property. The voltage is determined by the nature of the reaction, not how much reactant or product you have. In practical terms, as long as you've got enough of the reactants to make the reaction go, the electromotive force remains the same for the entire duration of the reaction until it runs out.
So the objective is to get right how much you need.
Yeah,
To
it
get
is.
the max amount of power.
Mm-hmm. Mm-hmm. So the idea is, can we pick 2 complementary reactions that will give us the amount of voltage that we need to run whatever it is we got to have? So, if we go back to this, what is the total voltage of this system? Well, it's 0.13 and 1.69, so that's 82?
Yeah.
1.82 volts. That's how much voltage this galvanic cell produces. Now the good news is, you can take several galvanic cells and hook them up in series, and you can add the voltages together. So if you take 6 of these things, you end up with a system that produces about 12 volts of electricity. Now, when you add multiple cells together, we don't call them cells anymore, we refer to the collection as a battery. A car battery is 6 separate linked cells that together produce the approximately 12 volts that your car needs to get started. What's that?
A lot of cells that Tesla flows through.
Well, there are other things we can do to accommodate that. For more information on that, take the E&M class from Mr. Summerhays.